So we're going to explore the really important concept of linear combinations. And first, I want to remind ourselves first that we can write out matrix multiplication using the following notation. So we talked about this in a prior lesson where we could express a system of equations using this format where we're multiplying column vectors A1 through AN times the variable matrix x1, x2, all the way up to xn. So here we have our column matrix that represents the variable matrix, and we also have the individual columns of our matrix A. So this is one of the ways that we talked about expressing a solution, and we'll use that to talk about what a linear combination is. Essentially, what we get out of this is a particular system that's listed in the form AX equals B is consistent if and only if it can be written as the sum of scalar multiples of the column vectors of A. And that's essentially what we've written out in this statement here. So this sum is then called the linear combination. And we'll work out an example where we can understand exactly how this works a little bit more clearly, I think. So here's what we're going to have as our example. We're going to take B to be equal to the column vector 3, 8, 1. And we're going to have A1 be equal to 1, 2, negative 1. And A2 is going to be equal to 1, 3, 1. And A3 is going to be equal to 1, 4, 3. And again, what we're after here is how do we show a vector B as a linear combination of the other vectors A1, A2, and A3. And we're going to do that by expressing B as a linear combination of the vectors A1, A2, and A3. So what that means is we need to find some scalars such that, and we'll call them x1, x2, and x3, such that the following is true. We want a constant times A1 plus a constant times A2 plus a constant times A3. And that should be equal to our vector that we're given here, 3, 8, 1. So this is what it means to be a linear combination. If it's going to be a solution to the system, it has to fit underneath this particular kind of an expression. So again, the question is, which constants do I have here? So I need to find some numbers that I can plug in such that when we multiply these up, it adds up to be 3, 8, 1, this particular vector. And that's really the goal here, is to write that vector as a linear combination of these three given vectors. So now that we at least sort of understand what it means to be a linear combination, the question is, what are these constants? And we could certainly try to do it by trial and error, and we might get lucky. In this case, I've designed it to be some nice integer values, so it wouldn't be entirely surprising to me if you were able to figure out what those are without doing any work. But obviously, in more complicated scenarios, we need to figure out what these values are. Maybe they're real, maybe they're even complex, but we still need to have a system for solving out where those are. Well, since we understand already that this represents a system of equations, we can multiply all this back up and put it as a regular system of equations. In this case, that would look something like the following: x1 plus x2 plus x3 equals 3. And the second line would show that 2x1 plus 3x2 plus 4x3 equals 8. And if we multiply up the third row, all of this stuff coming together into an equation, that means we're going to get something like minus x1 plus x2 plus 3x3 equals 1. So there's your third equation. So now I just have a system of equations. At this point, we can process this any way we want. Ideally, probably we would just put it into an augmented matrix and solve from there. So 1, 1, 1, 3, 2, 3, 4, 8, negative 1, 1, 3, 1. So we would get an augmented matrix like this, and then we would just row ref it, which we could do using Octave or an online calculator or something like that, or even our graphing calculators if we know how to use that, and get up with 1, 0, minus 1, 1, 0, 1, 2, 2, and a row of zeros along the bottom. And now we would go ahead and express this in its normal form with the variables back in. So let's go ahead and solve these out for x1, x2, and x3, and I've done that already. You have x1 is going to be equal to 1 plus x3. The second row is going to tell us that x2 is equal to 2 minus 2x3. And the third row says that x3 is free, so it's equal to itself. So in this case, there's infinitely many combinations that we can choose from to make this vector here, 3, 8, 1, a linear combination of the given vectors a1, a2, and a3. So if we wanted an example, we could just pick one. Any example would do. So just for example, let's go ahead and take x3 equal to 0. And that, of course, would imply that x1 is equal to 1. And we would also have from that that x2 is equal to 2. So I have a linear combination here that looks like this. 1 times a1, which was 1, 2, negative 1, plus 2 times a2, which was 1, 3, 1, plus 0 times 1, 4, 3, which is a3, and then that's going to be equal to 3, 8, 1, the given vector. So I have done what I set out to do, which was to write the vector 3, 8, 1 as a linear combination of the other two, which just is sort of a fancy way to say we're going to take multiples of these three vectors and try and generate the given vector here. So again, we found that there's infinitely many scenarios that will provide that. This is one particular example here. And you can see, again, we've written that in. And if you were to check this out, if you were to multiply all this up and add it together, you would find, in fact, that you do get the vector 3, 8, 1 from the left-hand side. I've got an example problem below. So see if you can follow that through again using the example and show that the vector 3, 9, 3 is a linear combination, or can be written as a linear combination of the vectors that we have here, these same three vectors.